Today, we're diving into a story about a technique to completely change the game in AI. It's about how a really clever mix of math and engineering took the power to build at the absolute cutting edge and put it on a single computer. This is how the ability to innovate was taken from just a handful of elite labs and handed over to developers and researchers, well, everywhere.
So to really get why this was such a revolution, you first have to understand the sheer scale of the problem. Look at this number, 65 billion. That's how many parameters a big, powerful language model can have. You can think of each parameter as a tiny little knob or a switch. Fine-tuning a model means you have to adjust all 65 billion of those knobs to get it to learn a new skill. And the amount of computing power and memory for that? Until very recently, it was just astronomical.
And then this happened. The number of high-end GPUs you needed to fine-tune that 65 billion parameter giant, it dropped to just one. I mean, that's the leap we're talking about. It went from a problem that needed a whole data center to something you could do on a single machine. So the question is, how? How is that even possible? Well, that's exactly what we're going to break down.
Here's our plan for today. First, we're going to look at what we're calling the billion-parameter barrier, the wall that stood in everyone's way. Then, we'll unpack QLoRA itself, the technique that just smashed right through it. After that, we'll get into the engineer's secret sauce, the stuff that makes it all actually work. We'll also look at some of the theoretical cracks in the foundation. And finally, we'll peek over the horizon to see what's coming next, beyond QLoRA.
Okay, so let's set the stage. Training one of these huge models from scratch can cost millions of dollars. But even just specializing an existing one, fine-tuning it, was a monumental task. You needed enough memory to hold the model itself, all of its gradients, which are basically the instructions for how it should learn, and all the data for the optimizer. We're talking hundreds and hundreds of gigabytes. This created this huge barrier to entry, a deep moat that basically kept this incredible technology locked away for a select few who had access to massive server farms.
And that brings us to the breakthrough itself, QLoRA. This wasn't just some small efficiency hack. It was a completely different way of thinking that unlocked these giant models from much wider audience. This is the technique that made fine-tuning a 65 billion parameter model a reality on just one GPU.
At the very heart of QLoRA is a concept called quantization. Here's a way to think about it. Imagine you have this beautiful, ultra-high-resolution photo. The detail is incredible, but the file size is massive. Quantization is kind of like saving that photo at a lower resolution. Yeah, you lose some of that super fine-grained detail, it gets a little bit blurrier, but the file size just shrinks dramatically. In AI, we're doing the exact same thing, but with the numbers that represent the model's knowledge, taking them from high-precision 16-bit numbers all the way down to tiny 4-bit numbers.
So how does QLoRA use this trick? It's this really elegant four-step process. First, you take your huge pre-trained model. Second, and this is key, you quantize it down to 4-bit, making it way smaller in memory. And then you freeze it. You make it read-only. Third, you inject these tiny trainable modules called adapters into the model, and these little guys stay at a higher 16-bit precision. And finally, you only train those small adapters. The real genius here is that you're separating the jobs. The massive, frozen model provides all the raw knowledge, while the tiny adapters are the only things that need to learn the new task.
And the results are just staggering. A full fine-tuning run could eat up over 780 gigabytes of GPU memory. QLoRA brings that all the way down to under 48 gigs. This literally took the process from the exclusive domain of elite labs and put it into the hands of individual researchers and developers. And the most important part? For a ton of tasks, the performance is just as good. This is what the democratization of AI actually looks like in practice.
But here's where the story gets even more interesting. You might think that clever algorithm we just talked about is the whole magic trick. Well, it's not. The reason QLoRA actually works in the real world comes down to some incredibly clever systems engineering. This is the secret sauce that makes the theory run without blowing up your machine.
Let me ask you a question. When you're fine-tuning one of these models, what do you think takes up the most space on your GPU? I mean, the obvious answer is the model's weights themselves, right? There are 65 billion of them after all. But that's not the full story.
Just look at this breakdown. The model weights are only about 15% of the problem. The real memory hogs are the optimizer's states. You can think of that as the algorithm's short-term memory, all the notes it's jotting down as it learns, and the model's activations, which are all the temporary signals firing between neurons. These things can cause these massive, sudden spikes in memory usage that just crash your training run with an out-of-memory error. And that is where these unsung heroes come in. This is the software stack that makes QLoRA possible. You've got libraries like bits and bytes doing the heavy lifting for quantization, and 𝗱𝗃 for handling the adapters. But the real game changer, the thing that often makes the difference between success and failure, is the use of paged optimizers. They are so clever. They watch for those memory spikes, and right before they happen, they shuffle some of that data from the super fast but very limited GPU memory over to your computer's main RAM, preventing a crash.
So the big takeaway here is this. Modern AI breakthroughs are not just about a cool idea and a research paper. They're a fusion. They're a mix of brilliant algorithmic design and incredibly careful system-level engineering. You can't have one without the other if you really want to push the limits of what's possible.
Now, as powerful and amazing as QLoRA is, it's not a silver bullet. It's an incredibly effective engineering solution, but it's not what a researcher might call theoretically pure. There are trade-offs and compromises happening under the hood, and understanding those is the key to seeing where the entire field is headed next.
This quote from the source material just nails the central problem. Those little trainable adapters, they're actually being forced to do two jobs at once. Their first job is to learn the new task. That's the task mismatch. But their second job is to constantly correct for the blurriness, for the errors that were introduced when we quantize the big model. Those are the quantization artifacts, and having to do both jobs at once creates a hidden problem.
So this leads us to the first major limitation. Because that huge base model is quantized and then frozen, any errors from that process are locked in. They are permanent. The adapters are then forced to work overtime, essentially fighting against this built-in distortion while also trying to learn the new skill. And that can end up limiting how well the model can truly perform at its absolute peak.
The second limitation comes from a core idea in the LoRA part of QLoRA. The low actually stands for low rank, and it assumes that you can teach a model a new skill with really simple, efficient updates. Kind of like teaching a master painter a new style by only giving them 2 new brushstrokes. Now, this works surprisingly well for a lot of things, but for really complex reasoning, the model might need to make bigger, more expressive changes. It might need a whole new palette and set of brushes. The risk is that the adapters are just fundamentally too simple, that the adaptation space they create is too small, which puts a ceiling on the model's true potential.
So knowing about these limitations, the obvious question is, where do we go from here? QLoRA kicked open a really important door, but now the entire research community is focused on what's on the other side. This is the next frontier, building on these ideas to create methods that are even more powerful and even more robust.
The next wave of innovation is going to tackle these exact problems. We're already seeing research into things like rank-flexible adapters, adapters that can actually grow and become more complex if a task demands it. Or things like sensitivity-aware placement, which very cleverly puts the adapters in the parts in the model that were most damaged by the quantization process. All of these are strategies to fine-tune more effectively and with way less distortion.
And this slide just captures the evolution of the whole field perfectly. The first challenge was purely about possibility. Can we even do this on hardware that people can actually get their hands on? And QLoRA screamed, yes, we can. But now the goal has matured. The new question is all about quality and resilience. Can we specialize these massive models efficiently without collecting all these damaging errors along the way?
So that's the challenge that lies ahead for the whole field. It's a brand new game where memory is the ultimate bottleneck, and efficiency is everything. QLoRA kicked open the door to democratized AI for sure, and the next breakthrough will be the one that makes that adaptation not just possible, but robust, powerful, and truly distortion-free.